number, like identify those hanging groups. I actually would do this one third and the other one afterwards. I would. 2, number the non-hydrogen groups that are hanging off. Number the chain. Then just make sure that you list them alphabetically. So I would say that this is really 1, 2, 3. I would really switch those. So the ones that I have up here, these are the only ones that you're going to see as groups hanging off of a chain that you should be able to name. So a single carbon hanging off is a methyl. A 2-carbon group hanging off, so that would be a CH2, CH3 hanging off like in one piece. That would be an ethyl. I don't really do the next one, but if you saw a CH2, CH2, CH3 group hanging off, that would be a propyl. The last one are the halogens. Halogens are pretty easy because halogens, remember, are in group 7. So they only ever form just a single covalent bond. And so they'll just be hanging off of the chain. They're not going to be like attached to multiple things. They'll only ever have one. So the way that you name those ones is you use the first part of their name and you just put an O on it. So the fluorine becomes fluoro, the chlorine becomes chloro, the bromine becomes bromo, and iodine becomes iodo. So those are like the non-hydrogen hanging groups you're going to see. So let's practice some of these because that's really the kicker. Okay? So in this one doesn't have anything except just carbons. In this I just put the carbons. Hydrogens would be here. So you'd have H's, they just get exasperatingly long, which is why I oftentimes leave them off. Right, so all those dashes would be hydrogens. But to be honest, you really don't care about those, right? Because when you name, you assume that all those hydrogens are there. So you look and find the longest carbon chain. And in this one, how many do you see? You see 6. So there's 1, 2, 3, 4, 5, 6. Okay. You may see, some people may, if you go this way, what's that? It's only 5. Don't do that one. Okay. If you went this way, that's 6. That'd be okay too. Okay. Because it wouldn't matter either you have that carbon sticking up or the carbon straight at the end. I always try to opt for the simplest one, but do make sure that you double check. Okay, so if it's 6, then that means that this is a hexane. So the longest carbon chain becomes the last part of the name. So all those hydrogens sticking off, the only ones you care about are the ones that are not hydrogen. So there's 2 groups that are hanging off of the chain that are not hydrogen that we have to name. So one is a CH3. So I said if you have a single carbon molecules are methanes, but if they're hanging off, then they are methyls. This one sticking down is a CH2CH3. It's a 2-carbon group hanging off of the chain, so you call that a ethyl. Okay, so step 1, find the longest carbon chain, circle it, that's the last word in the name. 2, circle non-hydrogen groups and name them. Step 3, I got to number this chain. So I'm not going to number the pieces hanging off, but I need to number the chain hexane so that I can tell where the methyl and the ethyl groups are attached. So I either number from one side or the other side of the chain. Which one would I do here? From the left or the right? The right. Why? Do you see that the first branch is off of the second carbon? If I come from the other side, it's the third one. So I would number, this would be 1, 2. So this is a 2, 3, 4. This is a 4, 5, and 6. So the number in front of the group tells you which carbon it's attached to. So the last thing is, since I have a methyl and I have an ethyl, then I have to go back and list them, and you always list them alphabetically. So which do you write first? So it'd be 4 ethyl, 2 methyl hexane. 4 ethyl, 2 methyl hexane. I don't like all the hydrogens, you can tell. These are all hydrogens, I just didn't even put them in. So you tell me on this one, what is the longest carbon chain? Longest carbon chain. I see more than that. Longest carbon chain. 8. Can you see 8? So follow the chain. It does not have to be in a straight line.
Just can't go down a dead end.
Correct. You're always, if it goes down a dead end and it's still longish, you're good. So I had some people said this, but that's only 7. Can you see that if I come down and up, that's 8. Get your longest carbon chain because it's always going to make it easier to name. So that accounts for all 8 of those carbons. So that would be called what? Octane. Right? Longest carbon chain makes it an octane. What's the only thing else I got to name? So you look, see all those H's? You don't care about those. But what do you see? Do you see this group? That's the only one I got to name. It's a CH3, so it's called a methyl. Last thing, the naming, the numbering. Which side am I going to start from over here? Or do I start over here? Start on the right side because the branch is closer. So just look at it. Always start from the side closer to the branch. So this would be 1, 2, 3 methyl. This would be 4, 5, 6, 7, and 8. So this is 3 methyl octane. Follow those same steps each way.
Well, can you go back to that? So that's methyl. Coming off the 3rd carbon. So it is called
3 methyl octane.
Methyl octane.
Yep. Make sense?
Yes.
All right. So let's just do a couple that have some of the halogens on them that have a fluorine or a chlorine or a bromine or an iodine. And then we're going to look at some different ways that you can see them drawn. So don't worry about this one. Do this one over here. I don't know why that carbon is red. I don't know. It just happened that day. It should be a blue one. There. Longest carbon chain. You're right. What did you see? 6. Okay, if you go straight across, it's only 5. 6 is the longest, so 6 makes this a hexane. So that takes care of all those carbons. So what is not hydrogen that I still have to name? The carbon over here. And this is a methyl. And there's a chlorine. So do check because it does look like carbon, but it's got an L. So that's how you've got to just double check and make sure you don't see it. So if it's a chlorine, you call this a chloro. So it just uses the first part. So I have chloro, I have methyl, and I have hexane. So now I've got to determine where do the non-hydrogen groups hang off. Which way do I need to number? Why?
Because it's the first.
Because chlorine's hanging off of that end. So this is 1, 2, 3, 4, 5, 6. This is a 4, and this is a 1. The number in front of the non-hydrogen group tells you which carbon it hangs off of. Last thing you have to do is list them how? Alphabetically. So which am I going to write first? Put the chloro first. So this is 1 chloro, 4 methyl.
so the top one is one,
Mm-hmm.
chloro, methyl.
It's off of carbon 4.
Hexane.
Yep. And you just write them all together. So you just write it out.
Oh, each branch, one
Uh-huh.
branch, second branch.
So other ways that you might see molecules drawn, don't like, okay? These are skeletal structures. Super simple for me to draw. This doesn't take, I don't get like hand cramps trying to put in carbons and hydrogens, but you've got to remember what this means, okay? So looking at this top left one, how many carbons in that molecule? Yes, okay? This carbon, 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 carbon. Every end and every corner is a carbon. The one sticking up is the chlorine coming off of the group, so that's not a carbon on that end. But look at the one to the right. How many carbons on that one? Yes. Okay. Can you count 11? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 11 carbons total in that structure. So if you see a line sticking up, what is this? It's a CH3, so it's a methyl group. So if you see a line sticking off of a skeletal structure, it's a methyl group. How many carbons in the next one? Mm-hmm. So you see that there's 6. The lines coming to the chlorine is the bond connecting the chlorine to that carbon chain. So if you have the chlorine and you have the bromine like the one down here, that line coming down is just the covalent bond attaching the halogen. But if you have a line sticking down with nothing on it, don't forget that's a chlorine or carbon on the end. So in naming, first one, what do I got to do when I name this one? Longest carbon chain is what? And so I still circle them. I still go in circle like my little zigzag because that helps me to see what's not part of the chain. It helps me to see what is hanging off. So this is a hexane. Yeah. Okay. Hanging off, this is a chloro, and it's sticking off of carbon number 2. I would say this is carbon 1, this is carbon 2. So nice when there's only one. You don't have to worry about the alphabetical, you just find which side it's closer to. What about the next one to the right? Longest carbon chain is?
11, 3, 4, 9.
No.
Oh, no, it's 8. So it's
8.
octane, but it goes straight across.
Go straight across.
So octane.
So octane. This we said is a line sticking up on a skeletal is a methyl, not an emethyl. And one here. And one here. What else do you have to include? Which way do I start numbering from? From the right, because that's closer to the branch. So remember that's carbon 1. And that's why I actually circle the zigzag to make sure that I number all the way across. Because I see people like wanting to start here because it's the first place where lines come together. Circle the longest zigzag part and then number. Okay, so that one is 2 and a 3 and a what? 4. So there's, this one would be 2-methyl, this is going to be 3-methyl, and this one's going to be 4-methyl. So when you have multiple of the same groups, you can pull them together. You just list the numbers in order. So this would be 2, 3, 4, and since there's 3 methyls, you call it trimethyl. It is a little redundant. 2, 3, 4, trimethyl octane.
Just 3 methyl groups. That's why I would be 2, 3, 4 methyl octane.
Correct.
That's why I write it all.
Uh-huh. Yeah, so put the tri in there. And IUPAC says you have to do that. It's not me. I think it's redundant. I think 2, 3, 4 clearly says there's 3 methyls. I don't know why you need a tri, but
There's 4 methyls.
you do tetra.
Oh, tetra.
Yeah, so you stick with the same, like the covalent naming. So you would have di would be 2, 3 would be tri, 4 would be tetra. I don't do that. That's just terrible. Okay, try one more. So this is a hexane. Yeah. This is a chloro. This is a chloro. 1, 2 di chloro hexane. Oop. That's my pen does that. I think I drag it, and so it does like a line. I like push hard and drag. Stupid. So this one to me, smiley face. Okay. So what's the longest one in that one? Where did you go? So you would just went straight 1, 2, 3, 4, 5. You went that way?
That way, and then I counted
Okay.
that way.
But then we've got these. Okay, so when you count, do you see that you could have gone this way?
Could have gone that way. That way.
In theory, you could have gone this way. Wouldn't that be 5? Yeah, and you could have gone this way. That would still be 5. It's not going to change your answer, right? So that's like there's a centerpiece and then 2 carbon groups sticking off in all directions. Okay, so and if given the option, I always choose for the straight line. It's the traditionalist in me. So 5 carbons makes this a pentane. What is this? No. A methyl would be just a line. That's an ethyl. Do you see that's 2 carbons hanging off here? This is an ethyl group. So if you see a line with a bend, that's a carbon, that's a CH2, and that's a CH3. Yeah. And so numbering 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 doesn't matter, right? Because it's all, no matter which side you go from, it's sticking off to the 3. So it'd be 3 ethyl pentane. I think this is the most challenging thing to do, is to look at a structure and figure out the name. Because there's so many different strange, twisty ways that you can actually have one drawn. What if you get the name? This is super easy. So if you get the name, what do you look for first? You look at the last words, right? So I go all the way to the end of the word and I see hexane. So hexane tells you to drop down how many carbons? 6. 1, 2, 3, 4, 5, 6. And the nice thing is you can number them left to right. 1, 2, 3, 4, 5, 6. You don't have to have them bending all around in crazy directions. You can just do them in order. So you can say, well, this is going to be carbon 1, 2, 3, 4, 5, and 6. And so then just add the groups onto their respective carbons. So off of carbon 2, I'll put a CH3. Off of carbon 3, I'll put a chlorine. Anything else? All the rest of that is what? This. Those are hydrogens. Okay? So 2-methyl 3-chlorohexane, look at the last word, number the chain, just add those groups.
So on the test, do you want us to specifically write out CH3 or
So
can we
it
leave the C there?
So it depends. Like you could now take this, you could do a condensed structure with this, much easier. So what would carbon 1 look like? Carbon 1, if it was condensed, would be a CH3. Carbon 2 would be what? A CH. And then hanging down would be a CH3. And then the next carbon 3 would be a CH with a chlorine sticking up. Carbon 4 is a CH2, 5, CH2, and 6, a CH3. Okay, so if you kind of draw out the framework of it, then you just remember you're anywhere that you don't have 4 covalent bonds, you're going to have hydrogens. Okay, so see on this one, I just put a carbon. Remember that carbon always has 4 covalent bonds. And in these, we're only talking about single bonds. So if I see a carbon linked to another carbon, I know there's got to be 3 hydrogens on that end. Okay, so I just added a hydrogen here, here, and here. So I added those 3. This one would be a hydrogen. These would all be hydrogens. So this would really be truly more closer to a Lewis structure versus condensed. And really, I just give you the option. I tell you, draw this molecule. You can write condensed structure. What if I did it in skeletal? How many lines in the zigzag? 5. Remember we said that with skeletal, there's always 1 less line than carbon. So I'd go 1, 2, 3, 4, 5, 6. Right? 1, 2, 3, 4, 5 lines. When I put my pen down, I say carbon 1. So I put my pen down and say 1. Then when I go up, I say 2. So every time I stop and do a corner, I count a carbon. Count those. Do you see 5 lines? Hexane, 6 carbons. Okay? Then what do I got to do? Line up off of carbon 2 and
line down on 3 and then Cl.
yep, and put a chlorine. Do you see that one? 1, 2, 3, 4, 5, 6 hexane, methyl off of carbon 2, chlorine off of carbon 3. Either one. Like when you have to draw them, I'll say like you can do either. I think like the condensed formula like helps me to check myself, put those hydrogens in there, but I'm fine if you do a skeletal. Here's a crazy one, 3,4-difluoro-7-ethyl-decane. I was like, I don't know what I was thinking. So all you do is look at the last word is this. So that is how many? 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Look at the last word, decane's 10. Okay, so I know that I am going to have bonds above and below. Right, all the way around. Carbon's always going to have 4 single bonds, so there's always going to be a bond up and a bond down, bond to the left, bond to the right. Doesn't matter, I being the traditionalist go from left to right in my numbering, so I would just go back and say, okay, well this is going to be carbon 1, 2, 3, 4, 5, 6, 7, 8, 9, and that one's going to be 10. Okay, so then just go and number from left to right. So off of carbon 3, what am I going to hang? So I'm going to put a fluorine on carbon 3 and on carbon 4. That is 3,4-difluoro. 2 fluorines, that's all that means. Just 1 on 3, 1 on 4. If they were both on 3, you would see 3,3-difluoro. Okay, so you do list those numbers. If it was on the same carbon and more than like 2 of them, you would actually list them together that way. 7-ethyl. What's an ethyl? We just put a CH2, CH3. It would be fine if you dropped it down or dropped it up, pointed it up or down, as long as you have a CH2, CH3 connected to the 7th carbon. Same thing with the fluorines. I wouldn't care if you put them both down. You'll see in labs, single bonds rotate. So we can flip things around, we can turn. Because they're all that tetrahedral shape, they have a lot of flexibility. Really, all I'm looking for is, do I see 10 carbons? Do I have a fluorine off of 3, a fluorine off of 4, and do I have an ethyl group off of 7? But all the rest of those things sticking out are all what? Yeah, all these are hydrogens. Any empty spots would be a hydrogen. So annoying.
You may have just answered it. The CH2 and the CH3, is it different if we write CH2 like that, or C with 2 H's coming off, a C with 3 H's coming off. Like,
Oh, like it, so you're saying if you did, the only problem with that is you'll just have to make this line longer so that they don't end up like running into each other. So you're saying doing it like this?
either way is acceptable.
Yeah. So that all I did was like, you have to extend the bond because otherwise your H's start running into each other.
But we can do
Okay?
that on-
You could do that too. Yeah, that's fine.
Cool, write that out.
So that, like that, is a complete Lewis structure. So Lewis structures have all the lines. Condensed formula, if I did this in the condensed formula, I would say CH3, CH2. What would be 3? CH with an F. 4 with an F. 5, 6. I'm going to drop it down. And then
So when you do on number 7, when you do the CH2, CH3, it has to be beside each other. You don't have
they
to
can
write
come
out-
down. They can come down, but space-wise, like if you have it like that, or if you had it like this, you can see they're same thing. It's just that most of the time they'll drop it down one and then keep going with it. Okay, just for a space aspect. But that's called the condense. Condense just tells you how many hydrogens are around each of those carbons.
So the bottom one is called condensed.
So this is the condensed formula. This is the skeletal. Ooh. And then this would be the Lewis. Different options. On your test, like this will be one of your short answer ones where I just say draw it so you can have it as long as I'm looking for, are there 10 carbons? Do I have the 2 fluorines on the right carbons? Do I have the ethyl
We
group
can
there?
use the skeletal, like out the first skeletal.
Yeah, very simple.
We can
Yeah.
do that or
Yeah.
Lewis or.
Yep, it'd be fine. But the thing is like when you see them, you need to be able to recognize like how to name them. Like if you see skeletal, if you see the condensed, if you see the Lewis structure, you want to be able to name them in all those ways. So that's why I try to like give you examples with all 3 of them, because your homework's going to give you examples with all of them. All right, one more. Cyclos. So crazy. Okay, so we did this in lab. So if you've got lab tonight, we're going to look at a cyclo. Cyclo is the ring structure, and that is the last part of the name. Okay, so what you do is you look and you count how many carbons that make up the ring, and that's the last part of the name. So this first one, what is it? It is a hexane, so you call it a cyclohexane because you're naming how many carbons in the ring. So that's the that becomes like the last name, like what we've been doing with all of them. That's the last name. If you see cyclo, then you know you're going to make it into a ring structure. If you see a ring structure, you know that it's going to have cyclo as part of its last name. But see, that takes care of all those carbons. The only thing I have to look for is anything that's not hydrogen sticking off. Is there anything? Yep. Do you see this one? It's a CH3. Do you see this one? Those are both methyls. All right, so I got a methyl here and I got a methyl here. So I know that I can put them together and call them dimethyls. But I got to say, which carbon in the ring is it? Now this one, notice there's no beginning and no end in a ring. You just get to pick a spot to start from. The goal is make the lowest number combination. You would always start with one of the branch groups. If there's only one branch group, that's where you start. If there's more than one, so I could start here or I could start here.
Then it would be the same because it's opposite sides.
Exactly. So this, if I say this is 1, 2, 3, 4, 5, 6, being the traditionalist that likes to go clockwise. Okay. I could go that way. If I went and started at the bottom and went counterclockwise, it still would be 1, 2, 3, 4. So I would still have the exact same thing on 1 and 4. So that wouldn't matter. So I would call this what? Yeah. Yep, 1,4-dimethylcyclohexane.
Would you ever have a CH3 in the number 3 spot? So if you count that way, 1, 2, 3. If you count the other way, 1, 2, 3, 4, 5.
Right, so you would do 1, 2, 3.
Okay,
So you would number, so you have your choice. Always start at the branch, and you're always going to figure out which direction you go to get the lowest number combinations. So like, look at the one over there. So that's a what? Yeah. Do you see this one? These are the two common ones. Carbon doesn't mind making a 5 and a 6-membered ring. So this is cyclopentane. What's the groups hanging off? Oh, you saw it. See, a lot of people miss that one. So this is a chloro. This is a, and this is a.
Well, can you start with one of them?
Would it be 1, 2,
Oh, they are.
They're on the same carbon.
Yeah, it should be 1, 2
So would you
dimethyl.
Not 2, because if it was 1, 2, one would be on carbon 1.
One dimethyl. No?
1, 1.
1 dimethyl.
That's
Okay,
exactly right. You always list all the carbon atoms that they're attached to. So this one, which one would you want to start with? Chlorine or the methyls? Start with the methyls, because that's going to make these two methyls 1, 1. If I started with the chlorine, then my methyls will be 3, 3. So I want the lowest possible numbering. So this is carbon 1. Which direction do I go?
Counterclockwise.
2, 3, 4, 5. That's a 5.
Oh, yeah.
1, 1, and that's a 3.
So you do 3 chloro.
Which, yeah, there's the last thing, alphabetical. So which do I list first? Chloro. 3. 3. That's the last rule. I know, that's the rule that most people want to list them by their numbers, but they put in that you need to list them by their alphabetical listing. So this would be 1, 1 dimethyl. Okay, I'm going to put so if you want to do more practice of drawing and naming, I'm going to put like another tutorial like I did in the first exam. There'll be another, say 20, 30-minute tutorial of going through them, just naming them, using different shapes, like using condensed, using Lewis, and then having you draw them based on the names. So if you're still, in Moodle. So for the first exam, I had like a out-of-class practice kind of thing that I did with unit conversions, balancing equations, things like that.
On Moodle?
Yes, in Moodle.
I totally.
Yep, all of my this is like all totally recorded, and all these videos are posted in
Yeah, I got
YouTube,
that part.
and you can find the links in Moodle. All of my PowerPoints, I mark them up and save them. They're also posted in Moodle. So they're listed as like chapter 4 marked up PowerPoint. So all this stuff that I've been writing, that's actually all on those PowerPoints too.
Yeah,
So if you ever want to go back and look and you're like, I don't know what I wrote, let me go look and see. You could pull mine up and actually see what I wrote specifically if you don't want to watch the video. Okay? But I'll put another one up tomorrow afternoon. Yeah, tomorrow afternoon, another like practice tutorial with naming. And so you can use that to help just a little extra practice with this. You guys seem like you've about got that. Okay? So no, we're not going to draw. I'll put ones like those in. So we got 2 more topics. Darn, I forgot that. We have 2 more topics in this, and one really kind of bleeds into the other. So isomers. Isomers are when you have molecules with the same formula, but they have either a different appearance or they actually have different bonding arrangements. So the key thing is isomers, same formula. Okay, so that's the key thing to remember. So for example, if I have C4H10, I have 2 molecules, they both have C4H10, I know that they're isomers. So one of them could be this, with all the blasted hydrogens. Okay, and what would that be? 4 carbon, it is butane, right? Okay, but what if I have this? Do you see that there's still 4 carbons, 10 hydrogens there? Does it look different? Like when you just lay it down on paper? It kind of looks, one looks like a little zigzaggy, the other one looks like a little long straight line. But if I had to name the longest carbon chain on that one, what is that? 4, so that molecule is butane as well. Da, 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 da. Oh, that H doesn't look like it's on top of the other H. There. How about this one? How many carbons? 10 hydrogens. But what's the longest carbon chain here? 3. So do you see that the longest carbon chain is 3, not 4? But it's still C4H10. So this one, is it butane? No. 3 carbons in a row would be what? Propane. And this group sticking up is a methyl. So this is 2-methyl propane. These are isomers. They have 4 carbons, 10 hydrogens. They either have different appearance or they're actually put together differently. The first 2 look different but have the same name. So the first 2 are called conformational isomers. So this one, the straight one, and the one that looks like a zigzag, they call these conformational isomers. They look different on paper, but they have the same name. They're actually the same molecule, just bent around different. But these 2 are not the same. Butane and 2-methyl propane, they're actually different bonding arrangements. They have different names. Those are structural isomers. So that should be an M.
So conformational is the same molecules, right?
Uh-huh. It's the same, they just look different. And how do I know for sure that those 2 are the same molecule?
The molecular formula is the same.
Molecular formula is the same, that tells me they're isomers. But how do I know that those are conformational isomers? What did I have to do?
Oh, they have the same name.
They have the same name. Conformational isomers have the same name. So that's really the key thing with isomers, just name them. Okay? So if you name them butane, butane, you're like, oh, that's the same. Even though they look different, I could twist one and make it look like and make it into the other one without having to break any bonds. The other 2, though, butane and 2-methyl propane, I can't rotate, twist, flip the molecules around because they have a different bonding arrangement. Those are structural isomers. So those are actually 2 different molecules. They may have very different properties.
Oh, they're dependent on the structure.
Yep. And again, if you name them, the names are different, you know they're structural isomers.
So
Make
they
sense?
have different bonding arrangements or structure.
Correct. Okay. So look. So there's their examples. So here's an example of a conformational isomer pair. So you see 4 in a row, that's butane. You see 3 in a row, but then another carbon sticking up off the end. So don't make the mistake and say that that's only 3. Make sure that you always find the longest carbon chain. So you see that those are both butane. Conformational isomers, they're just drawn differently, same molecule. Okay, so those are like the things that you ask. So here, I want you to draw 3 structural isomers of C5H12. So C5, what could you do?
3 long bound,
Do 3
3, 4,
regular.
and 5.
What would be like, what would be the carbon arrangement of one of these?
Straight line.
Straight line, okay? So everybody got this? I could go like this. 5 carbons in a row, yes? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Those are hydrogens, not putting them in. Okay? So everybody agrees that's C5H12. So how can I rearrange these carbons, and this is pentane, how could I rearrange these carbons so they're not all in a straight line? Take one off. 1, 2, 3, 4. Where do you want me to put it?
Anywhere.
Where up top? If I put it here,
Not
not on an end, where do I want to put it? Okay, one of the middles. Uh-huh. Okay, that's now a what? That hanging off is going to be a methyl. Uh-huh. So this is going to be a 4-carbon molecule. This is a butane. This would be a 2-methyl. See, there's still, if you go through and count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, still 12 dashes off of my carbons, still have C5H12, but this one is actually going to be 2-methylbutane. This is pentane. And this is really one of the ways I know that these are structural isomers. They have different names. They have different bonding arrangements, so they're different molecules. But they do have the same number of atoms. They have the same formula. Yeah. We can do one more, too. So I could do what? Ah, genius. Huh? Uh-huh. So is that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12? 12 hydrogens? 2 what? It's a name 3 carbons in the longest chain, so that would be a 3 propane. And then hanging off above is a methyl, below is a methyl, and those are on carbon number 2 dimethyl propane.
What's the structure of just that regular propane gas that we burn?
Just 3 carbons in a row, flat. Just not in a branch. 3 carbons in a row. CH3, CH2, CH3. That's propane. Like what's in your hibachi grill, yeah. Or if you go buy a 20-pound tank.
I couldn't see it unless you circled it. I had it circled in my head.
Can you see that this is 3? That's the propane. Then here's the methyl, and here's the methyl. So that's 2,2-dimethyl propane.
Is that always in a gaseous state?
These all are, unless you pressurize them, because they're really super small. Okay, so methane is natural gas. Butane is in your Bic lighter. The only reason that butane's a liquid is because it's pressurized. And when you press down the little lever, it lets out the pressure and the gas comes out. So it converts from liquid to gas. So these structural isomers. Okay? And so all you do is just sort of like try to rearrange the carbons to try and form a different shape, like a different connection. So those of you that have lab tonight, we're going to work on those ones too. Okay? Don't want to look at that. You tell me, are these molecules structural, conformational, or not related? So how do you determine if they are isomers at all? What do you have to do?
They're molecular form.
Right. So count the number of carbons. Tell me how many carbons in the first one? 8. So how many carbons in the second one? 8. Okay. So I will just tell you, if they have, since they're all single bonds and there's no ring structure, if they have the same number of carbons, they're going to have the same number of hydrogens.
As long as
Okay?
they're not ring structure.
Correct. If they're ring structures, they're going to have 2 less. But for this, it's always twice the number of carbons plus 2. Because remember, there's always a hydrogen above and below along the chain, and then there's 1 on either end. So if you take the carbon number times 2 and add those ones on the end, that's how I figure out the formula. So you don't have to count those. Okay? Yep. So carbon number times 2 plus 2 tells you the number of hydrogens in all the single chains. And we're not going to worry about doubles. We're not going to do double bonds. We're not going to do triple bonds. We're not going to do oxygens or nitrogens or sulfurs. Nope. This is like as complicated as our naming gets. Okay? So now when you look at this, So yes, they're isomers. That's what you know. So you know that they're related because they're isomers. So now the question is, are they structural isomers or conformational isomers? And truly, the only way to know is to do what? You got to name them, okay? Name the top one, name the bottom one. If they have the same name, they're conformational. If they have different names, they're structural. So figure out what's the longest chain in the top one? 6. Okay, does everybody find this?
Yes.
Okay, so 6 makes it A. XA. This is A, and this is A. Which side do I start numbering from, or does it not matter? It doesn't matter, because I go 1, 2, 3, 4. So this one's on 3, this one's on 4. If I flipped and numbered the opposite direction, it would still be 3, 4.
So 3, 4 down there.
What about that one? Longest chain? 6. Exactly. That's good. Okay, so they're the same name. Did they look different when I first flipped it and you looked where you're like, oh no, those aren't the same at all, okay? And so you're gonna see that. That's the key. The key is just sequentially go through, find the longest carbon chain, circle the non-hydrogen groups and name them, number the chain, list them alphabetically, and do it for both of them and you'll be able to figure out.
Would you ever give us the name where we have to find that and then tell you if it's structural?
No, I would give you, I have, most of the ones that I do with this are like, here's 2 molecules. Are they which one are they?
Are they in Dutch? What form are they in? Like,
They'll be like that. They're condensed.
you can't have any skeletal.
They are, skeletal's easier for me to draw, I'll just say. Because I have like a drawing program, so I can make some zigzags now. Like, it's not that bad. All right. No, we're not. Those ones I'll put up. Okay. Conformational isomers, structural isomers. These, so we did the rings, okay? So we did some ring structures. Ring structures lose their rotation, okay? So when you have a long chain, single bonds rotate. So single bonds have the ability to flip and switch their structures around. When you make a ring, it locks it into place. So if you have any hanging groups, if you have 2, they're either locked both pointing the same way or both pointing different ways. And so I brought an example because I didn't break them on the way here. I brought one. Where's the other one? Oh. And this, and I'm not going to ask you to name these, but you see the same thing when you have double bonds. So my example here, so this is a 2-carbon group, and see the double bond? Okay, so these are going to be fluorines and these are going to be hydrogens. But if you look, see I can't twist it? Okay, when I have single bonds, see you can rotate? So if it's a single bond, I have this rotation. As soon as I make a double bond, it's stuck, okay? So it becomes stuck in a position. So do you see how these 2 similar atoms are on opposite sides here? The atoms are on the same side, okay? So both of these are both on the same side of the double bond. Here, there's one down and one up. That's what these are, okay? So I didn't bring a ring, but we're actually gonna do this in lab. And so in this, with this one, and this is a cyclopentane, here, there is a methyl group, and they use the wedge and dashes to try and show that 3-dimensional shape. A wedge means it sticks forward. A dash means it sticks backwards. So this one, can you kind of see how this is sticking up and that's pointing down? So these are on opposite sides, but see how these 2 both point down? Those ones are on the same side, okay? The one on the same side is called cis. The one on opposite side is called trans. So which one is cis? When you look at these 2, this one. Because both of the same atoms are on the same side of the double bond. But this one is trans. I always remembered it because I always think of cis's on the same side, and those are all S sounds. So cis's are on the same side. And I always think of trans, like Trans-America, you go across America. So trans, I always think of across. So trans is always like opposite sides. So you can see that with these. So this one is going to be trans, and this one's going to be cis. But other than that, they're the exact same molecule, but their hanging groups are stuck in position. So both of those would be 1,2-dimethyl cyclopentane. If you look at that one, see the cyclopentane, ring of 5. 1,2, because it would be on carbon 1 and carbon 2, and there's 2 of them. So they would both of them would be called 1,2-dimethyl cyclopentane, but you would put a trans out in front of the one on the left and put a cis out on the one on the right, because they exist in that structure. So there they show this one, trans. Over here, cis, with an S. They call those stereoisomers. So the way that I will draw them, so that it makes it really clear, I use the wedges and the dashes. So if you see 2 wedges or 2 dashes, which is it? If you see 2 wedges or 2 dashes connecting the groups, then you know that means they're on the same side. If you see 1 wedge and 1 dash, then that's trans. Because I think that makes it really obvious and clear, and you're not like, I don't really know if those are pointing up or down. That way you know they're sticking forward or they're pointing backwards.
Is that only with the 2?
Only with ring structures. It's the only time you're going to have to worry about them, because we're not going to name these. We don't name the double bonds, okay?
Only if there's 2.
Yep, and you'll have to have 2. If you only have 1, then it doesn't matter.
Then it's not top left.
Right. But if you have 2 hanging groups, you can name them by their cis or trans conformation. Okay? Everybody's like, oh, geez. Geez, why?
I don't like chiral.
Hmm?
I don't like the chiral one.
That's the last one. Okay, so the last thing that we're going to cover is what he doesn't like. These you do not have to worry about. I am not going to cover the functional groups in this chapter. I will include the functional groups as we find them while we're going through. Okay? So for you, you can list 4.3 functional groups. Don't worry about them. The one that I want to go through, none of this. I'm going to pull these out so you won't have to look at them again. They're kind of cool, but we'll get there. No, and these are lipids. And we will talk about lipids in the next chapter. So the book splits lipids into 2 parts. I'm just going to cover lipids together in chapter 5. Yeah, if you haven't done those, don't worry about them. It's kind of like when we skipped the half-lives and I just didn't count those. Okay? So you're okay with that too. There. Last page. Yep. Okay? So the last thing, and it's something that we actually talked about in lab, the last thing is talking about a special kind of isomer, and it is seen when you have these special carbons. And I have these. I have caraway seeds and I have spearmint, and I forgot to bring them with me. But you kind of know what they smell like. So molecules that have identical ways that they're put together can have really different characteristics. And this comes from the type of carbons that they have. So the carbon that I'm talking about is one that is described as being chiral. Okay? So I've heard some people call it chiral. That's fine if you want to pronounce it that way. Okay? Chiral is the way that I've always heard it pronounced, but I have heard other instructors say that, and I was like, what? Like they call the VSEPR, they call it Vesper. And I was like, no, that's not what you're saying. But that's just me, because it just depends on where you actually learned it. Just made me laugh when I heard that. Huh? Mm-hmm. Do what? Yeah, I know, and that's what they call it, the Vesper. So, chiral. This is what you look for. And these are going to come into play in carbohydrates, in proteins. We're going to see them again. So that is really the reason to make sure that everybody's got this part. Achiral carbon is one that has 4 single bonds, and all the groups connected, right and left, top and bottom, are different. Not just the atom right next to it, but the entire group on the right, the left, and the top and the bottom, like when you draw it like a Lewis structure. So notice in this one, this is a chiral. That black carbon in the middle is a chiral carbon. So this black carbon in the middle is here. There's an OH group above. There's a hydrogen here. Coming down, there's a CH2, CH3, and going to this side is a CH3. But when you look at and try to figure out if you have a chiral carbon, you always look at the entire group above, below, to the left, and the right. Okay? You don't just look at the atom right next to that carbon. It's the entire group. So in all cases. But now, there's a carbon here. Why is that carbon not chiral? See the one on the left? It's a CH3, so it's got 3 hydrogens. So the rule is all the groups have to be different. So a methyl group can't be chiral. It's got 3 hydrogens. You have to have 4 different groups. What about this CH2 down here? No. Right? Because it's got 2 hydrogens, and this CH3, no, it's got 3 hydrogens. So those ones are easy. If you see a CH2, CH3, you automatically know those are not chiral. Okay? It's when you only have a C with a whole bunch of other stuff, or you only have a CH, then you got to do all this comparison. So here's the ones to look at. So look at this top one. So in each case, you're comparing every single carbon in the molecule. So what about the first one, the purple? No, it's got 3 hydrogens. What about the second one? No, it's got 2. Third? No. Fourth? No. Your hydrocarbons are never chiral, okay? Because they've always got more than 2 or more hydrogens. So none. Okay? Pretty straightforward. Look at the one over to the right. So here, what about this one? No, it's got 3 hydrogens, okay? What about the one on this side? No, it's got 3 hydrogens. What about the one in the middle?
No.
Why?
Because it's CH3 and CH3.
Yes, do you see that this and this are the same? The right side and the left side are both CH3s. So there, and then the top is an OH and the bottom is an H. But it's not because these 2 are the same. None. So there's not that common. You don't see chiral carbons left and right everywhere. You do see chiral carbons in a lot of sugars. See the one that goes up and down? So that's our first sugar molecule. So that is a ketopentose. So it's a sugar. Look at the top one. Now this one, it doesn't have the hydrogens separated out, but does it have more than 1 hydrogen? Yes. So see CH2, if you see an H2 or an H3, exit off immediately. Okay? You don't have to worry about it. No, not chiral. Okay? 2 hydrogens. What about this one?
No, because they're missing another bond.
It's got a double bond. No double bonds, no triple bonds. Okay? Double bonds and triple bonds cannot be chiral. You have to have 4 single bonds. That's the first rule. So what about this one? This group, this group, this group, this group. Are those different? Do you see that? Above, I've got a 2-carbon group with 2 oxygens and 3 hydrogens. Below, I got a 2-carbon group with 5 hydrogens and 2 oxygens. Do you see above and below they're different? Left and right, I have a hydrogen and an OH. So those, yes, this is chiral. Okay, so when you're looking at these, you're not just looking at the atom next to the carbon, you're looking at the whole group. Okay, so I am comparing everything above, everything to the right and everything to the left, and everything below. Can you see that those are all different? The bonding arrangements above and below are not the same. Ooh, the bonding arrangements above and below, no, that way, sorry, are not the same. The number of atoms above and below that carbon, not the same. So let me change colors. What about the one below? What about this one? To the right is a hydrogen. To the left is an alcohol. Below is a CH2OH. And above is the 3-carbon group. Are all those different? Is this, this, and this? Are those different?
Yes.
Yeah. Okay, so the things I circled in purple, the whole group above, below, left, and right, yes. This is a chiral carbon. So the carbon that I have with the red, the carbon I have with the purple, those are both chiral carbons. What about the bottom one? CH2OH. Yep, 2 H's. So CH2, automatically, nope, not chiral. So this one is and this one is. Very common in sugars because sugars have a lot of hydrogens and alcohol, OH groups. And so there's a lot of chiral carbons. Okay, let's look at the one that's above right here. CH3. No, okay. CH3's got 3 hydrogens, not. What about this one? What about that carbon? Why? So on. Okay, but it does. So you see it's a CH. So in reality, that H is up here. Right? So that H would make the 4th. Remember, carbon's always got to have 4 covalent bonds. So I've got CH3 to the left. There's a hydrogen. There is a alcohol group. And then this 2-carbon group on that side. Is that chiral? Yeah.
So if it were just to have been H, it would have been no.
If it were just to have been H, what do you mean?
Like, I mean C.
Oh, if it was, it wouldn't because I would only have 3 bonds. It's got to have 4. Carbon's got to have 4 covalent bonds. So what about this one right here? So let me change color. You can see it. So now I'm looking at this one. So this hydrogen would be one that would be like up here. So I have a CH3, I have an OH, I have this big thing over on that left side, and I have an H above. Do I have 4 different groups? That's chiral as well. What about the last carbon? CH3. No. CH3? No. More than 1 hydrogen. You don't look at chiralness with oxygens. Oh. But here's the skeletal structure that he might enjoy. So every corner and every end is a carbon. I'm not going to ask you one like this, I promise, but I will show you. These are all carbons, right? So all the corners along in there, those are all carbons. Carbon has to have 4 bonds. So this carbon, how many hydrogens would this carbon have to have? This one. So you see that you see 2 bonds sticking off, so the other 2 bonds are hydrogens. So this is a CH2. So can you see that it's got to have 4 total? So what about this carbon right here? It's got 1 hydrogen sticking off. What about this carbon right here? It's going to have 1. Because see, you can only see 3 lines connected. The 4th one's got to be a hydrogen. It's not going to go around with 3 bonds. It's got to have 4. But this one...
Does that mean that's an improperly drawn skeletal?
Skeletal structures, remember, don't put hydrogens in.
They just have the...
The only reason you see the OHs is because those are alcohol groups. Those aren't just hydrogens.
So
Okay?
when it's not named, the connection is always an H.
Right. If you don't have 4 covalent bonds for visible on a skeletal structure, you've got to add in hydrogens if you're trying to figure it out. So would this one be chiral? No, because it's got 2 hydrogens, right? So it's CH2. There's 2 hydrogens on that one, so this one's a no. What about this one?
No, because you got 2 carbons.
No, it's not 2 carbons. So remember, I've got to count this whole thing, this, and this whole thing. Are all 4 of those different? So that one's chiral. This is vitamin C. Vitamin C has a chiral carbon. It's ascorbic acid. So what's important about this? You're like, stop. So what's important about this is drugs. Lots of drugs. No, what's important about this is that a chiral carbon, you can make the mirror image of a molecule with a chiral carbon, and it's not exactly the same. So if you have a chiral carbon in a medication, like a drug that's developed, you have to make sure that all of the chiral carbons get tested. So here's one, for example. So in this one, Parkinson's disease is characterized by an increase in tremors. So a person becomes more and more difficult for them to control muscle movements. And they have found that it's because of lack of or loss of dopamine in the brain. But dopamine is also very important in mood and memory. So another side effect of Parkinson's is that the patient starts having signs of dementia, that they have erratic emotional behaviors, they're depressed. All of those go right hand in hand. So what they found is their brain stops making dopamine, so they can give that patient a medication that gets converted to dopamine in the brain, and it helps to relieve those symptoms. So it allows the brain to form dopamine even though it's not making it itself, so it's sort of giving you the drug for it. So the medication they found is called DOPA. And so what they're showing up front, up at the top, is the chemical, and it's this carbon right here. Do you see that this carbon has this big group here, a nitrogen group, a group with a couple of oxygens, and a hydrogen? So the fourth one, see, you only see 3 lines. That fourth line would be a hydrogen. Can you see that all 4 of those are different? That's the chiral carbon. So if you make the mirror image of that, they had to actually go back and test those. They found that if they gave the patient one form, they improved. Their symptoms were alleviated. If they gave them the mirror image, it didn't do anything. It didn't work. And so that led to this understanding, well, there's got to be something, because like the molecules look the same, except that there are these mirror images at the chiral carbon. So L-DOPA is the one that they give Parkinson's patients. D-DOPA doesn't make any difference at all. Acetaminophen, which is Tylenol. Tylenol has one chiral carbon. One form of Tylenol reduces pain, reduces fever, reduces inflammation. The other form doesn't do anything. And it's because of that difference. So one form has all of the benefits. The other form, the opposite or the mirror image, has no effects. Which is oftentimes the case. And so I was making them in lab do this. It's really the best way to think about chiral carbons. I say chiral carbons is like handedness. When you look at your hands, they're right and left, and they're mirror images, yes? Like I can't take my left hand and lay it on my right hand and make it match exactly. And that's the same thing with chiral carbons. If I put them here, my pinkies and my thumbs are matched. If I put it here, then my fingertips and my wrist end up being that way. If I flip it over, that's the back of my hand and that's the palm. So it's still not the same. So very much of these medications react with or bind to structures in the body, and the shape is the important part. And so if you shake the hand of the person next to you, so if you shake, you always shake right hand and right hand, okay? That's normal. But what if you shake right hand and left hand? How does that feel? It's like, I don't want to do that. So, and that's the difference. So this is like, this drug reacts fine with the receptor in the body. If you have the chiral mirror image, it doesn't work. Okay, it doesn't have the same effect. And they actually found a really sad thing that happened. In the 1950s, in Europe, they were working on medication to try and alleviate morning sickness. Okay, so morning sickness is a negative thing because it's all based on hormone levels, but it's a problem in the first 3 months because you may lose weight. And really, what are you trying to do at that point? You're really trying to improve neurological development. You're trying to make sure that all of baby's parts are developing. So if you have a woman that's super sick, then that may actually have a negative effect on baby's birth weight, on development. Okay, so they were working on drugs trying to alleviate morning sickness. And what they did is they isolated or they synthesized this drug called thalidomide. And thalidomide, see the structure above. Thalidomide has a chiral carbon right here. So one side has this weird looking group, one side has this weird looking group, And then there's got the other one in, it's just the way that you would actually like look at it this way, one you would look at it that way, and then the hydrogen. Still that one chiral carbon that is present there. So they tested it and they were like, it reduces morning sickness. So women like gained weight, they maintained normal healthy weights in that first trimester, they saw better outcomes. So they were like, all right, let's scale up and we'll begin to distribute it. When they scaled up, so in small scale doing their drug testing, they only made one of the forms. So they call these forms enantiomers. They made like the left-handed form. They didn't make the right-handed form and test it. They only made the left-handed form. And at this time, they didn't require that you actually submitted the chemical structure of the molecule like they do now. So they went through testing. Everything worked really well. They scaled up. And they ended up making both enantiomers. So they made the left-handed chiral form and the right-handed chiral form. The problem is the right-handed chiral form is teratogenic, which means that it causes birth defects. So this was given in the first trimester, and they found that this actually stopped elongation of limb buds. So normally in those first 8 weeks, so between 8 and 10 weeks, so baby gets like these little buds. Okay, so you get little arm buds and you get little leg buds, and then those begin to elongate, and then you begin to have the forms of the arms and legs. So that happens in that 6 to 10 week span. Women that took thalidomide ended up with babies that had little flipper arms, that had abnormally shaped, super short limbs. About 10,000 babies were born in the 1950s. This was mostly in like Germany, Austria, mostly in that Eastern European area, because that's where they did the testing and that's where they really began to spread it. So what happens is you give it to women in their first trimester, you don't know that they have birth defects until when? Until they give birth, right? So it's another 6 to 7 months later. So in that time span, more women had taken thalidomide. And so over about a year to a year and a half, suddenly you have babies, their worst case scenario, like their GI tract didn't seal. So they ended up with like the anus and the urogenital openings didn't ever close completely. Better case scenario, they had some amounts of arms and legs, oftentimes much more sort of stunted looking. They were never able to walk. They never able to feed themselves. Most of them didn't live to maturity. They didn't live to adulthood. About 50% of them survived. So this was like a huge wake-up call for drug companies. You can't just make something and then say, yeah, this is good. You got to know the chemistry of it, okay? So having any kind of drug that's made now, you have to submit the chemical structure of your drug. And if there's any chiral carbons, you have to synthesize all of the forms that you could have, and they all have to be tested. So thalidomide, they actually use thalidomide now. They can synthesize just the one form. So they can synthesize this, and they do use it as an anti-nausea med for cancer patients. But they're extremely careful about giving it to any females because of that risk. It has like a really bad rap. So, and with good reason. So they have used it, especially with cancer patients that like nothing else is working. They can use thalidomide to help alleviate the nausea and everything associated with it. But it still is really kind of a taboo thing because that was a big outcome from like a big mistake. So now the FDA requires all of that testing occurs.
So now we're good enough with the chemistry. We could make it so that you only have
Yes.
the left-handed.
Mm-hmm. And they do use thalidomide, but it is with like reservation type of thing because that was such like 10,000 lives that are affected. That's a big number to just like suddenly have drop in 12 to 16 months. So by the time they pulled it off the market, I mean, then there was a lot of women that were pregnant and like knowing that was probably them.
Did they test the animals first?
Yes, but see, so they tested the left side. They didn't realize that they hadn't actually synthesized both forms. They only synthesized the left side and ran it through testing, and it worked great.
When they scaled it up to industrial.
When they scaled it up,
they got mixed.
then they got a half and half. And so, you know, when you make a small thing, you can use one process. When you scale up and suddenly you're making thousands and thousands of pills, then you may have to change your process because it's so much larger. So when they changed their processing to synthesize the drug for large scale distribution, they ended up making half and half. So that's sort of a consequence of like understanding the way that these organic molecules are made up and sort of how they're put together and how much of an effect that can actually have.
So they can make a small amount of drug and be careful that it's only on the left side.
Yep.
But if they're gonna make a whole lot, there might be some on the right side too.
Yeah, but they've like gone back, and so I know that now they do have thalidomide, that it's only that left-handed form, not the right-handed form, but they still don't use it large scale. Like they, just because of what happened in the 1950s. Like doctors just are like, no, we're not gonna prescribe that because that was really bad what happened.
So the point is, if they made a whole lot, the one on the left,
Mm-hmm.
it would be costing so much money because they have to make a whole bunch of little
Right.
amounts of it.
So there is that difference, but that's sort of the application for that. So stick with the stuff that we've talked about in this. The